This video is going to give an overview of directed acyclic graphs, or DAGs, and this is a visual representation of the relationship between variables, and this can be really useful in identifying confounding that is more convoluted than your typical confounding triangle. It's also useful for identifying other forms of bias, such as collider bias, and it's useful in identifying relationships that you might not have thought of when you're just looking at it in narrative format, such as variables that need to be included or intermediate outcomes between your exposure of interest and your outcome of interest that might be easier to measure. So an overview of what we're going to talk about is we're just going to cover an overview of DAGs, so the different components and some of the terminology. We're going to discuss direct and indirect effects and how to identify confounding and collider bias in DAGs, and the minimally sufficient set necessary to control confounding without necessarily controlling all confounders. And this DAG exercise is just in the slide deck because I was using this for the class ITA, and we're not going to talk about that here. So, like I said before, a directed acyclic graph is a visual representation of a relationship. So in this case, it's the relationship between occupation, smoking, and lung cancer. And these arrows are shorthand for a directional relationship. So for example, here it's the relationship between occupation and lung cancer, specifically the influence of occupation on lung cancer. The D in DAG is directed, so when I say that, I mean that the arrows have a head and a tail. There are scenarios where there's two heads. I'll get to that later. But typically each arrow has a tail and a head, and that indicates that the tail variable is having a influence on the head variable. So this is a directed path. So occupation has an effect on smoking, which has an effect on lung cancer. The A is acyclic, and this is an example of a relationship that loops back on itself. So x3 makes its way to y, and then y loops back on x3. And this is kind of a problem in DAGs, and you might be able to come up with some relationships that have a positive feedback or negative feedback relationship. But if you kind of break it down, what's happening here on the left is really shorthand for what's happening here on the right, where there's an x variable at one time and an x variable at another time. An example of this is high BMI causing someone to exercise less, which might lead to high BMI and even higher BMI. But because this is a time-dependent variable, this x, BMI, x at this time and x at that time are really viewed as two separate variables, and in that way we're able to keep this DAG acyclic. So the first of our terminology we're going to talk about is how we refer to these arrows. So we call them edges or arcs, and they represent a directional causal relationship from tail to head, so occupation leading to lung cancer. This is a shorthand for that relationship, and it's important to remember the directionality of that arrow and the implications for what that relationship is representing. So here it's not talking about how smoking can influence occupation, it's how occupation can influence smoking. And there is direct and indirect paths. So occupation here has both a direct and indirect path to lung cancer or outcome. So its direct path to lung cancer might be if you're exposed to fumes in your occupation, and that might cause lung cancer. And as I kind of alluded to earlier, a DAG can be useful in identifying intermediate outcomes where it might not have been as obvious to you at first how many things come in between this, such as occupation being related to exactly what part of that occupation you're in, different levels of exposure for different sections of the work environment, and even more proximate to lung cancer is stuff like the actual damage to the DNA. You're able to have many intermediate outcomes, but For simplicity, a good way, if you're interested in occupation and lung cancer, is to just represent it like this, and there's a lot implicit in this arrow that's in between. Um, but yeah, back to what I was saying, that's the direct path. There's also an indirect path from occupation to smoking to lung cancer. So there's certain occupations where smoking's a bit more common, and someone who didn't smoke might take up smoking for the social aspect, and that might lead to lung cancer independent of the occupation itself. So that would be the indirect path. And when considering the total effect of occupation on lung cancer, it's important to consider both paths it takes. When you're modeling this relationship by modeling occupation, it automatically accounts for this, but there might be situations such as mediation analysis where you're interested in the relative contribution of both these paths. Um, but yeah, no, that's something to consider. That a lot of times there's multiple paths from a variable to the outcome, and the total effect of that variable is the combined effect of all the paths. So an ancestor, we're getting into some relative terminology. That's terminology used to describe where one variable is relative to another. An ancestor is anything upstream on the causal path. So relative to lung cancer, all three of these are ancestors. But if we're talking about just smoking, the only ancestor would be anxiety. A parent is something that is one step on upstream on the causal path, and a grandparent is something that's two steps upstream, so a parent of a parent. There's very similar terminology for downstream stuff. So um, here you'll notice both smoking and lung cancer are descendants of anxiety, but occupation isn't. And the reason for that is occupation's not directly on the causal path from anxiety forward. Um, there is a path to it, but it's not directed. It goes against the grain on this arrow, and that has some implications later on that we're going to talk about. But for the sake of this, we can just suffice to say that occupation is not a descendant of anxiety. In reality, it might be. Some jobs are more stressful than others, but just for the sake of this DAG to illustrate this, I could have just called this like X1, X2, X3. It's just to show what it looks like when something is down the path but not on the causal path. Uh, so, and again, similar to the upstream terminology, there is child, which is something that is one step downstream, and grandchild that is two steps downstream. This is relative to anxiety. Unmeasured variables you'll sometimes see just represented with a U, and this U might have a dashed line. Um, and this is really common in epidemiology, especially if you're using data that was collected for other reasons, that you're now kind of inheriting that data and using it for something other than its original purpose, or if you're using hospital data from administrative data collection. There's a lot of times there's stuff that's really important to the relationship that you don't have access to, but nonetheless, it's worth including in the graph so you can make decisions about how you're going to approach that and do things like bias analysis. And that's typically what this U represents whenever you see that in a DAG. So a bidirectional arrow is something that I've seen students tempted to use to represent something that is just an association that's not causal, something that is an interaction, or even a positive feedback relationship. But the most appropriate way to use a bidirectional arrow is when two variables share an upstream uh, parent. So Z2 and X share an upstream parent. And shorthand for this is to just have a bidirectional arrow between Z2 and X. Um, so yeah, that would be a way to explicitly show that they share an upstream parent, but not draw that in. A non-directed arrow. This one is dashed. I don't think they always need to be dashed. I think that's just kind of the convention. Generally means that two variables are related for reasons other than a causal relationship or having a shared ancestor, like I said before. Um, and a really common example of this is collider bias, something that I'm going to get into a bit later. Um, Not fully, but in the context of DAGs. And like I said, or I guess I didn't say it, there's no real way to interact or to represent interaction in a DAG. There are I DAGs, like there's interaction DAGs, but as far as just regular DAGs, there's no way to explicitly show that there's an interaction happening. So this is kind of a classic interaction example where it's common knowledge that smoking causes lung cancer and semi-common knowledge that asbestos causes lung cancer. But one of the main protective mechanisms that's built into every human is the cilia, like the cilia in the airways that is able to bring any debris in the lungs that may be carrying asbestos and have you cough it up. But if you're a smoker, generally, well, these are often paralyzed, and that permits asbestos to get to the lungs more efficiently and into the alveoli. So the relationship between asbestos and lung cancer might be stronger among smokers rather than non-smokers, and that is a very good illustration of interaction. And unfortunately, there's no proper way to represent this in a DAG. You'd have to basically recognize that whenever two variables both terminate at the outcome, there's kind of implicit possibility that there's an interaction happening. And if you don't make that known through annotation or in the figure, the reader can assume there's no interaction. But if you do annotate either in the DAG or in the figure description, then that's where you show that there's an interaction happening. But unfortunately, there's no way to do that that is formal as far as anything written. So this is your typical confounding triangle. Some of you may have seen the C more in the middle with an arrow going off in either direction, but I prefer to have the C upstream of both the exposure and the outcome. And that's just me. I like it just because it makes it explicit that the confounder comes temporally before. I just like all of my tails to be on the left and all of the heads to be on the right, if possible. But this is a really simple example of confounding where you probably wouldn't need a DAG to be able to visualize this relationship and point that variable out as a confounder, but it can get more complex with backdoor paths, where here there's no variable that's going directly to x and directly to y, but this z1 variable here has a causal directed path to x and one to y. So controlling for z1 would be something that's necessary that might not have been obvious until you put this DAG together. And I don't know if I said it, we refer to this as a backdoor path. Yeah. So collider bias is something that I'm going to talk about now, where basically two variables have an association only by virtue of having a common child. So this is an example where let's just assume there's zero real relationship between attractiveness and talent. But if your sample is just famous people, you're going to find talent and attractiveness overrepresented in that group, in that subset of the human population. And that might lead you to believe that these two traits are related because they're occurring together in famous people. But this is an example of collider bias where this kind of spurious association is generated between these two variables. Collider bias can create confounding bias, which is a serious issue when that happens. So here, there is no confounding happening here. This Z1, Z2 path is not influencing our XY relationship at all. But let's just say we had a collider here, and we conditioned on that collider. So say we stratified on it or we matched on it. We have created a relationship between Z1 and Z3 that wasn't there that opens this backdoor path all the way back to Y, and all of a sudden we've created confounding that wasn't there. So you might see blocked and unblocked in the literature referring to DAGs. This is an example of a blocked path where we haven't touched anything yet. We're just leaving it how it is. There is no bias here because it's only when we condition on this collider, like I said before, like including it in the model or matching on it or something like that, that all of a sudden we create this artificial relationship uh, between these two variables, and you've unblocked a blocked path. So by taking action on a blocked path, such in this way, you're unblocking it and creating a backdoor path. Um, Here, this is just the one I showed before. This is an example of an unblocked path where Z1 has a path to X and one to Y, and you should take action to eliminate this path rather than leaving it be. Where if you control for Z1, then you eliminate this biasing path. So the minimally sufficient set is something that is a very important concept. I'm going to get into why. So basically, this if we're interested in this XY relationship, we're trying to isolate that. There's three confounding paths. There's this first one with Z1 going to X and to Y. Similarly, Z2 going to X and going to Y. And this third one where Z3 is going to X through Z2 and to Y. It's tempting to just throw all three into the model or match on all three or something to control for that. There's some reasons that that is not the most efficient way to go. If we were to control for all three, that would be perfect. That would be fine. Like it would isolate this XY relationship. But some of the problems with that are we tend to try and go for the most parsimonious model possible. That's more of like the epidemiologist view of regression. A statistician might not be as worried about that, but the fewest number of variables we can have in our model to adequately control for confounding, the better. Um, and as soon as you're doing something like matching or stratifying or something like that, as soon as you're including another variable, these subsets of covariate patterns and match groups and or frequency match groups are going to get smaller and smaller because you're going to get really specific here. You're having a lot of things that you're conditioning on to be included in the study, and also variables are sometimes in the study planning stage really expensive to gather data on. So if you can control all the confounding by just collecting data on two of them. If that third one's expensive, that would be ideal if you can just get away with it with just the two. Um, so an example of a minimally sufficient set here, although there's three confounders, we can eliminate all of the biasing paths just with Z1 and Z2. So you'll see, let's put those in the model, and the way I showed that happening is just kind of deleting them from this causal diagram. So we got Z1 and Z2 in there. Now Z3 is still out there. It's still but it's not having an influence on X because we blocked its path to X. So although Z3 has been left uncontrolled, it's no longer a confounder. Well, it's more it's technically still a confounder because these things are still there. We just controlled for them, but it's not creating a confounding path. So we found a minimally sufficient set in Z1 and Z2, where in a situation where there's three confounders. So that's a huge thing. Um, Last thing, this is a kind of upcoming topic in epidemiology in general, where Um, the conventional like definition of a confounder is just if it causes X and it causes Y, it's a confounder, and you control for it by throwing it in the model, and that was just kind of this like dogmatic way of viewing it. Um, but that there are specific situations where that's not the call. So I kind of showed it before, where here we have a few confounding paths between X and Y. And it might look like C makes a good minimally sufficient set, or if we control C, all of a sudden um, Z1 is related to X, but it's blocked. The path to Y is blocked, and Z2 is related to Y, but the path to X is blocked, and C is controlled. So we'd say, nice, that's a good minimally sufficient set. But something we talked about before is it creates conditioning on that would create a backdoor path. So the minimally sufficient set where confounding paths are blocked and we didn't create any bias would actually be conditioning on C and one of the other variables, so Z2 or Z1. And yeah, I hope that was helpful.